Hello, my name is Michał Kowalski and I'm a PhD candidate in Doctoral School of Exact and Natural Sciences at Jagiellonian University. I'm doing my research in Bioinformatics Research Group under supervision of Dr. Paweł Łabaj, and today I will be presenting our latest results in the topic of in silico evaluation of SARS-CoV-2 primers performance. On the right side of the slide, you can see the stack plot of the clade allotment through time, which is highlighting the magnitude of variability of SARS-CoV-2 through the course of the pandemic. Such variability raises need for constant sanity checking of measures of precaution and diagnostic methods all around the world. The idea behind our research was motivated by an observation of growth of false positive and false negative results obtained with RT-qPCR tests. We've also were tracking mutations in a whole genome perspective and noticed the presence of unamplified regions, gaps in row and consensus sequences that have been produced with amplicon-based methods on newly emerged lineages and clades. We had wondered if the primer design is standardized enough, if the cyclic in vitro validation of primer sets wouldn't be an expensive venture, how rapid will the evolution of SARS-CoV-2 be in the future, and if there is already software that would allow us to benchmark primers in silico. After thorough research of related literature and tests of currently widely used software, we placed a couple of hypotheses. First one stated that the performance of PCR family primers can be measured in silico, and we decided not to use multiple sequence alignments to be able to simulate all of the possible binding sites of primers within the mixture. Second one was about the structures of currently recommended sets, that some of them may be in fact corrupted and lead to homo and heterodimerization events. The last one stated that the SARS-CoV-2 primer probe set's performance can actually be altered through time because of the evolution of this virus. We had constructed a dataset consisting of high-quality SARS-CoV-2 genomes from GIS8 repository, applied quality filters discarding sequences with more than 5% of ambiguous nucleotides, and genomes that were incomplete. Then we had developed a Python library directly for the task of benchmark of qPCR primer probe sets, and performed the benchmark twice with two policies: no mismatch allowed and up to 3 mismatches allowed. Additionally, we had incorporated the Vienna RNA package 2 to analyze structures of primers and their dimerization properties. During this presentation, I will focus only on the no mismatch policy, since we had observed that even one mismatch can alter the performance of primers. On this logo plot, you can see one substitution at position 1400-143. The standalone mismatch caused all the problems with amplicon-based sequencing, producing gaps in ORF1a region in all of the sequences from patients that belonged to the same medical cohort in Poland, despite only 10% of probability of occurrence of this mutation. The results of our benchmark had determined the 5 potentially best sets of primers for diagnostic use. As shown on the left, their performance has indeed been changing through the course of the pandemic. The overall performance, being in line with last sliding window, is a pure coincidence. It is important to have in mind that the eSarbeco set is actually a screening set that can catch sarbecoviruses, and as I tested with BLAST, also a couple of other beta coronaviruses. What is concerning is the difference between the overall intersection of all 5 best primer sets over the union of their performance, which is bigger than 100,000 sequences. The performance of all primers on clade level varies clade by clade. 5 sets that came up as last in our benchmark has been most susceptible to the evolution of the virus. In the middle of the heat map, you can see also decrease in performance of the US CDC and Institut de Pasteur primer sets. On lineage level, the impact of evolution on the performance is even more visible. The US CDC N3 set, which in fact was retracted almost a year ago, couldn't match almost any sequences from the B.1.5 to 5 lineage. The modified version of the RDRP primer, recommended by the World Health Organization, couldn't recognize almost any sequences from the B.1.617.2 variant, which is also currently known as Delta. Modification in the RDRP primer was introduced as the amendment to the original release. The original simply had a typo in it. Having in mind also reports about false positive results, especially for the US CDC and gene sets, we had decided to predict their secondary structures and dimerization properties to perform an investigation that is not based on the viral evolution. Each slide with presented structures will contain a probability of binding scale calculated from the minimum free energy with usage of Vienna RNA2 package. The retracted US CDC N3 set is actually not showing any visible destructive dimerization properties that could cleave the dye and the quencher, yet it can still produce false negatives with the heterodimerization events. The reported for hetero and homodimerization events US CDC N2 set, which is currently still in use, also has relatively non-problematic structures. On the other hand, the events has been reported when it was used with the US CDC N1 set, but the cross set dimerization is still under our investigation. In regards to the false negatives, the same observations as with N3 sets are valid. The example of the most problematic structure lies outside of the US CDC group. The structural corruption of the probe of Hong Kong University and gene set is clearly visible just by its standalone structure, but the homodimer of the probe really highlights its magnitude. These observations are leading to the following conclusions. Further use of primer sets which are most susceptible to the evolution of SARS-CoV-2 should be discontinued. We need to approach the challenge of increased genomic variability by validating primers periodically or with the emergence of nucleates and lineages. The efforts to create standardized ways of primer validation and their design, as well as laboratory protocols, are being made. The initiatives regarding primer sanity checking have already raised up, by the example of GISAID Primer Checker. This research was supported by Alcira Denis Herzog Silva Beneficent Association, the Polish Ministry of Science and Higher Education. It was also partially funded by Polish Medical Research Agency within the Genomic Epidemiological Surveillance Project, and also was greatly supported by the members of MetaSAP Consortium. I would like to thank all of the MetaSAP experts, especially from Brazil, USA, Sweden, India, and Poland, for their expertise and meritorical support. I would also like to thank the GISAID initiative and the submitters for aggregating and sharing epidemiological data. Thank you very much for your attention, and if you have any questions, do not hesitate to reach out to me. Thank you once again.